In section 9.2, we're going to look at a concept known as the composition of functions, primarily in order to talk about inverses. It's going to be a definition that we need to talk about inverse functions, where inverse functions are really the most important thing that we have to cover out of 9.2. The reason why we stick 9.2 in here is so that we can see what the connection between exponential and logarithmic functions are. Now, there's plenty of applications just on the concept of composition of functions and for inverses, but we're really wanting to answer the question of how do we invert an exponential. And what I mean by that is in the same sense that we can square a square root to cancel out the radical. We did that in chapter 7. We can cube root a cube. Whenever we have an equation where we're trying to solve for x, we very often do the opposite operation to move things from one side to the other. If I have x plus 3, I'm going to subtract the 3 across, because subtracting 3 is the inverse of adding 3. Alright, and so we're going to need to define what the inverse of an exponential is so that we can solve equations that involve exponential expressions. Section 9.2, composition of functions and inverse functions. Let's begin by defining what we mean by the composition of functions. The composition of functions f and g is given by the following expression. Okay, this is read as f composed with g, and what that means is, and this is a little circle, it's kind of like a degree symbol, but it's not raised up into the superscript, it's just a little circle. It doesn't mean O as in fog, it's f composed with g. Now this is the name of the new function, and on the right hand side is how to find it. You'll remember that in function notation, the thing inside the parentheses is what you plug in for x, and so what this expression tells us to do is to find f composed with g. We take the whole formula for g and plug it in to f. Okay? Now let me walk through that with this example below here. If I have f of x is equal to 5x plus 6 and g of x is equal to x squared minus 1, then by definition f composed with g is f of g of x. Now what is g of x? G of x is this expression right here, right? So I'm going to find f of x squared minus 1. Okay? So what does it mean to find f of x squared minus 1? It means to take this expression and substitute it in for x here. So replacing x with x squared minus 1 is how I get f composed with g. Okay, and then if I just multiply this out, combine like terms, I end up with 5x squared minus 5 plus 6, or 5x squared plus 1. Alright, so f composed with g is a new function of x that looks like this. It's 5x squared plus 1. Okay? That's how we find the composition of functions. In example B, we're looking at finding g composed with f. It's the backward question, right? Above we were looking at f composed with g. Now we're finding g composed with f, and realize this is a different question, right? Instead of asking for g to be plugged into f, we're going to find what is g of f of x. So we're going to take f of x, which is 5x plus 6, and we're going to stick that into g of x. So everywhere there's an x in g, we're going to replace it with 5x plus 6, right? Here's what g looks like, right? Whenever you start plugging things in, that's where the x was. So here's what I'm going to plug in. I'm going to plug in 5x plus 6. Now with just a little bit of algebra, we multiply this out FOIL style, so we end up with 25x squared plus 60x plus 36 minus 1, which gives me 25x squared plus 60x plus 35. Just in case you didn't see that, that was 5x plus 6 times 5x plus 6 FOIL. That gives me this expression right there. And that's how we plug one function into another. I want to do one more example, very much like the last example that we did. We were given two functions. F of x is equal to 4x minus 7, and g of x is equal to x plus 7 divided by 4. And we're asked to find both f composed with g and g composed with f. F composed with g of x is going to be f of g of x, meaning f of x plus 7 over 4. Okay? So we're taking this expression and plugging it in there. So that means 4 times x plus 7 over 4 minus 7. Now the 4's cancel, and I'm left with x plus 7 minus 7, which leaves me with x. Okay? Now notice what that says is f composed with g of a number is that number. Okay? Now the long way about thinking of this is that f composed with g means first take a number, plug it into g, get the answer, plug that answer into f, and see what you get. But this work that we just did shows that whenever I plug a number into g and then the answer into f, I get back what I started with. In effect, f canceled out what g did. Now let's look at the reverse question. G composed with f. Now you're not always going to get the same answer. Like we saw in the previous example, we got two different formulas when we did f composed with g and g composed with f. So we have to check and see if we get something different here. G composed with f is g of f of x, which is g of 4x minus 7. Now that means I'm going to take 4x minus 7 and stick it in for x here. So I have 4x minus 7 plus 7 all over 4. The 7's cancel, and I'm left with 4x over 4. The 4's divide out, and I'm left with what? X. Again, g composed with f of some number is that same number. So notice that if we let, say, x equal 2, what is f of 2 for these formulas? F of 2 would be 4 times 2 minus 7. 8 minus 7 is 1. Right? So take that 1 and plug it into g. What do you get? Well, g of 1 is going to be 1 plus 7 divided by 4, which gives me 8 divided by 4, or 2. Notice that's the same number that I started with. And that will happen for these two functions. That will happen with no matter what number you start with. You start with 75, 21, whatever. You apply one function after another, you get back to x. That's in fact, you're always going to get what you started with. So that implies that f undoes g and vice versa. Now that we've seen these types of functions that reverse the effect or undo other functions, we're ready to talk about, or at least give that concept a name. We call those types of functions inverse functions. So any two functions that reverse the effect of each other are called inverses. That's an informal definition, but more mathematically speaking, we're saying that if I take f of g of x, I get back with x, and if I take g of f of x, or g composed with f, I get back to x. So here are some examples of some inverse functions, right? And you should be able to kind of get the hang of this pretty quickly. X plus 3 is a function. Okay? It is in effect adding 3 to a number. If I give you a number, this function adds 3 to it. Okay? What's the inverse of that? What's the opposite of adding 3 to a number? Well, it's subtracting 3 from a number. Those are inverse functions. Okay? What about 2x? 2x is in effect multiplying a number by 2. So what reverses that? What undoes that? What's the opposite of multiplying by 2? Well, dividing by 2, right? So x over 2 would be the inverse function for that. And what about squaring a function? Well, the inverse of that is the square root of x, as long as we assume x is a positive number, because if x is negative, then those don't reverse the effect of each other, as we saw back in chapter 7. But for positive numbers, they are inverses of each other. It is important to note that not all functions have inverses. Some do, and some don't. So how do we know when they do and when they don't? Well, there's a property that a function has that we refer to as one-to-one. So they have inverses when they are one-to-one. So what does one-to-one mean? What does it mean for a function to be one-to-one? Okay, it means that if each value in the range corresponds with exactly one value in the domain. Okay, now range is the numbers you get to, the output of the function. Okay, so what we're saying is that if you get a particular output from a function, there is one and only one input that gets you there. So not two different inputs can't have the same output. Okay, and one way to check that is something called the horizontal line test. Now, you may have heard of something called the vertical line test. We use the vertical line test to decide on whether or not something is even a function. The horizontal line test is to determine whether or not something is one-to-one. Now, here's how the horizontal line test works. Okay, consider a couple of different functions. Here are my axes. Say I have a curve that does this. And let's take another function on a Cartesian graph. And that curve does this. Okay? The property that this function has that this one doesn't is that for any given height, right, any value on the y-axis, there's exactly one input x that gives me that height on the curve, right? For every horizontal line, it intersects exactly one point. Okay? This passes the horizontal line test. Okay? Meaning only, or I should say it this way, every horizontal line intersects the curve at most once. Could not intersect it at all, say, a curve that doesn't cover the entire y-axis. Now this one over here would fail. Notice if I draw this horizontal line right here, I've got 1, 2, 3. So that fails the horizontal line test. So this function over here is one-to-one. This one is not one-to-one. This function on the left has an inverse. The function on the right does not have an inverse. Okay? Now let's draw my axes again in blue. Alright, here we go. So here's a curve you may recognize. Right, that's the exponential. Is it one-to-one or not? It is. It passes the horizontal line test. Okay? How about this curve? Let's draw my graph. Sorry, I should have made that straighter, but hey. How about this curve here that does... That's the whole parabola, right? Is that one-to-one? Nope, it's not. That's why whenever I had the x squared function up there before, I said it only had an inverse if you looked at the right-hand side, meaning where x was positive, just this piece right here. If you consider the whole parabola, it's not one-to-one and it doesn't have an inverse. Okay? So the last question to answer then is, how do we find the inverses? How to find inverses. Okay, now here's the analytical technique. I'll come back and give you kind of an anecdotal approach, but the mathematical step-by-step process procedure for finding this is the following. What I suggest you do is, if you have a function, you want to find its inverse function, and you know that it's 1-to-1. So assuming that it's 1-to-1, we can do the following steps. Replace f of x with y's, with a y, then swap all the x's and y's. Replace the x with the y's. Solve for y, and once you have it solved for y, you're going to replace y with this symbol, okay, which is the notation for the inverse. So how do I find the inverse of 5x plus 1? So start by replacing this with y. So I have y is equal to 5x plus 1. Now step 2 says swap the x's and the y's, which means everywhere there's an x, put a y. Everywhere there's a y, put an x. So I have x is equal to 5y plus 1. Now solve for y. Subtract 1 from both sides. I have x minus 1 equals 5y. Divide both sides by 5. That gives me y is equal to x minus 1 divided by 5. And then I can write down that that is in fact my inverse function. Okay? And that's mathematically, procedurally, how we find the inverse function. I will point out that we can do this almost by just looking at the problem. Think about what this function does to a number. If I give you a number and you evaluate this function, what are you doing? Like if I give you 2, what's f of 2? Okay, well, first thing you do is you're going to plug in the 2 where there's an x, right? What's the first operation you do? You multiply by 5, right? So you multiply by 5 and then you'll add 1. So if you want to undo that, it's a lot like putting on your socks and shoes. I like this illustration because it gives us a little practical way of thinking of this, but the socks and shoes method for finding the inverse is, if you're going to put on your socks and then put on your shoes, how are you going to get back down to your bare feet? Do you take off your socks first or your shoes first? You undo it in the opposite order, right? So you put on your socks, you put on your shoes. If you want to take them off, you got to take off your shoes and then take off your socks. Right? So if I first multiply by 5 and then add 1, the inverse of that is going to be undo the adding of 1, which means subtract 1, and then divide that whole result by 5. You get x minus 1 all divided by 5. And that's how you can see that that is in fact the inverse function that you get. Now that doesn't always work. You get complicated functions and you get a mess, but in this simple case you can kind of confirm just by looking that that is in fact the inverse function. Okay, one more example just for good practice. We'll have f of x is equal to x cubed minus 3. We want to find the inverse function. So start by writing as y equals x cubed minus 3. Swap the x's and the y's. So that's x is equal to y cubed minus 3. Solve for y by adding 3 to both sides. Get x plus 3 is equal to y cubed. And then take the cube root of both sides, because that's what inverts y cubed. So you have y is equal to the cube root of x plus 3, or f inverse is the cube root of x plus 3. And there's your inverse function. Okay? All right, that's the end of section 9.2.